So the idea is that this is a panel, and we have several people with who have done work on this general topic here as part of our session. And so I thought the way we'd work this is I'd make some opening remarks, then turn the floor over to each of to those presenters to just present some of their own material as they see fit, taking something like on the order of 20 minutes to half an hour, depending on how much time they need. And then at the end, we'll just open it up for a general discussion about this this overall theme of kind of the theme is with this strange word that we've produced by contraction here that building agent models from conventional models. So I'm going to make my slides go full screen here. And so by agentization, we really mean using usually ABMs, but using kind of just some kind of computational reproduction of some existing models. So you in this version of how we do how one might do social science, we would simply take an existing model as a given, and we say it has a certain set of results, it has a certain set of statistical properties, whatever, and then we say, well, can we reproduce that if we render it with our computational agents? Now, it may be, in fact, that that's easy to do if the underlying mathematical model is written in terms of kind of the same primitives that we would use in ABM, or it might be harder to do if that was not the case. But so let's go through kind of the spectrum of the things that are possible this way. One goal of this approach, of course, is to assess the overall robustness of those well-known or kind of like possibly canonical models that we're all taught in the social sciences. That is, it's oftentimes very hard to relax mathematically certain behavioral specifications, networks, specifications, etc., but easier to do that computationally. Now, it may also be that the reverse is true, that some things that you can write down simply mathematically, like optimize, maximize something, are a little trickier to do computationally because the vagaries of our large scale models or something. But in general, we'll say that we'd hope to. The idea is to try to reproduce the conventional result, and then relax the specifications that produce the conventional result. That's the basic idea. And I think it's quite clear how to do this in the case of experimental and behavioral economics, right? In that world, in fact, the whole point of both those subfields within economics is that we don't really believe the underlying rational specifications. So let's put in something more plausible. But of course, there are a whole another number of other specifications having to do with networks and who interacts with whom and for how long, and solving for equilibrium, etc., that are also relevant that we might want to relax. And then I've written here this idea of Stu Kaufman's. Stu is kind of fond of talking about the adjacent possible, and by that he really means well, the way nature evolved is nature does not typically make large jumps. I mean, that's Darwin, but so nature explores. There's some complicated genetic structure, and then through various reproduction schemes, nature can sample nearby designs, as it were, for an individual. The word design is problematical in this regard, I suppose. Nature samples nearby configurations of genetic material. And in the same way, I mean, we'd like to be able to assess or sample nearby configurations of existing social theories, and that's hard to do mathematically often, not always, but often. But it's relatively easier, I think it's fair to say, to do computationally. We can have a debate about that. Maybe that's one thing we can discuss in our panel. And then, of course, I mean, just by way of extension, then one thing that we're not really talking about with agentization necessarily is, take a large jump from some existing model. That is, to kind of say, here's a whole new social phenomenon I want to explain. How does it relate to the existing theory? I mean, I guess we're not thinking about that as agentization right now, but that's really what many ABMs do today is you start afresh with a new specification and you just go off and see what your model says. But here we're really saying, well, let's hew quite closely to the existing world of theory and of well-known models. Say. So the recipe then really is just pick one of those models that has provable properties, whether they be analytically deducible. There's theorems about them, whether there be statistical properties that are understood, and then build an ABM that really just reproduces it. So, jump through all the hoops that are necessary to render the model with an ABM, and just show that the ABM does produce things that are, in the same ballpark, if not exactly the same outcome. Now, of course, with the ABM, typically we're going to have to put in numbers, we're going to put in specific parameters. So we'll always be open to the question as, the model that's purely symbolic may be more general than our ABM, but of course we can sample broad parameter spaces with enough compute time, and we can usually assuage most people's fears that the model, is or is not reproducing the conventional result. Then the real power of the approach, I think, is to demonstrate that we can generalize, or we can move beyond the conventional specification. And for example, one thing that might fall out is that the original results do occur, but maybe not on a time scale of interest to us. Either it takes a long time for them to appear, or maybe there's other problems with how long it takes these things to work out. For example, some of you will know that there are models in game theory that are formally ergodic, thinking about Peyton-Young's perturbed game theoretic models. But then those can display broken ergodicity. There's broken ergodicity, that term from condensed matter physics, I believe, most commonly used, or from spin glasses, where you would say that yes, things are formally ergodic, but on time scales of human lifetimes, they're not, or human societies, they're not. So in essence, they're broken ergodic in that sense. So we can learn about time scales when the conventional model is only an equilibrium model. We can learn about time scales if we, for example, know an initial condition that's not an equilibrium, and how we ask the question how long it takes to get there. It's also the case that we would also be able to sample specific parameter ranges where maybe the theoretical model is going to have going to work for all parameters, or for wide sets of parameters. I mean, like I showed yesterday in my discussion of firms. I mean, the set of all American firms is not is a very specific set tied to some very specific parameters. It's not that an abstract model of all firms would be of interest to the American economy. I mean, the American economy has certain parameters that make it something we would like to study specifically, at least for policy purposes. And then to generalize that specification and see what happens. I mean, and what can happen. I'll go through some just broad ideas in a second, but to say that I think to one of the authors of of some canonical model, it should be quite exciting actually to have your model reproduced with an ABM, precisely because you might learn something that you didn't know about your model before. And let me just report the fact that I'll report that when we ran a couple-day-long workshop on this idea back at the start of the semester, back in September, and for that workshop, I invited several well-known authors of conventional models, of analytical, mathematical, statistical models, to basically comment on agentized versions of the models. And I'll just report here, and probably this will come as a little surprise to those who have not heard it before, but about some fraction of the authors were in fact quite interested in seeing what happens to their model when it was agentized. I'll just report that Darren Acemoglu, for example, was quite excited to learn about Elaine Reed's agentization of the Acemoglu and Robinson model of democratization. So that was heartening to hear that. But by the same token, another group of authors were less excited to find out that whether or not the famous paper on which some of their notoriety stands, may or may not be as robust as they thought. So I got two classes of responses with very little in between. Basically, very excited, count me in, or I'm not interested, or of course just neglected my inquiries as well. So, anyways, I mentioned that just to say that I think that this approach has potential, and I think we're just at the dawn of trying to invoke it or use it in this way, and so it remains to be seen, I think, to what extent the authors of those conventional models will be willing to play nicely with us or not. Well, no, that remains to be seen. Okay, so what happens when you agentize a model? I mean, what can happen? Well, I've written here, just I'm going to put labels on Venn diagrams in essence. ABM is a special case. It is. And apologies for the notational terminology, probably more coherent in economics. But N stands for a neoclassical result, and A stands for an agent-based result. So it could be right that there's some neoclassical model. It's quite general. It works. It's proved in symbols only. For alpha, beta, gamma, ABC, something. It's and all we can do with the agent model is show that we have a special case of this. And the agent model, of course, is always numerical. It always has specific parameters. So we just basically always reproduce the conventional result. Because you can imagine a wide variety of things that would look this way. And then, I mean, one immediate issue is, could you relax the parameters and get outside that to move the A so it's outside the N? But for now, let's just imagine that no matter what we do, we always have the ABM as a special case of the neoclassical model N here in Venn diagram terms. But it could also be the case, and here I imagine, imagine that we've shown that ABM can be a special case, but now we're relaxing the specification and we find, holy cow, there actually is part of the model outcome space that is not accessible to the neoclassical specification, right? Because it uses rational agents, because it uses a network or it does not use a network. And that as soon as we add that feature to the original model specification, or we relax the original model specification, we get results that are now no longer the same. And so that here, the agent-based model and neoclassical model overlap, but the agent-based model can tell us something that the neoclassical model can't. The neoclassical model, in its generality, can do things that the agent-based model can. And I should have also explained that by neoclassical, I mean kind of the reigning paradigm within economics, oftentimes called today neoclassical economics, in opposition to classical economics, which by the way, one of our speakers, Jonathan, will be speaking to here in a moment. Now, ABM is generalization, meaning we also could have the following situation, where we could have the case where the agent-based model really does things that the neoclassical model can't, and subsumes all the neoclassical results, right? So here, the agent-based model is can be parameterized in ways that anything that can be done with the neoclassical model can be done as the agent-based model. In this sense, you would say, well, maybe the neoclassical model is a satisfactory explanation. Now, however, right, there are things that there are configurations of the social world outside the neoclassical model that it cannot really address, and we can only get at those through the agent-based model. And then another variant here is that the ABM is really distinct from the neoclassical model, and I've written here, right? This goes a little bit against my original formulation, which I said the goal of the agent-based model is to reproduce the neoclassical model. But once again, maybe we do that only for very specialized parameters. And then once we have put in what we really either believe to be or have empirical evidence for are the empirically valid parameters, the empirically reasonable parameters, it might be that the agent model is just outside the realm of the neoclassical model. And so this is, in this case, the ABM is distinct from the neoclassical model, even though it has the same kind of underlying parameterization of it. And I read it here, the open question is, what does the real world look like here? I'm calling E the real world. The real world may overlap with the agent-based model or not. And so, I think with this spectrum of possibilities here, we can imagine a variety of different things happening here. And what I would like to do now is to turn this discussion over to some specific examples of models that have been agentized. And some of the authors have presented these results earlier, but I think they probably had a little bit of time to work through some of the details now. So we'll have today, Jonathan will talk to us about a classical economic model that he's agentized. And then Jack Stevenson will tell us about an ecological model that was rendered in equation-based terms, but which he's done now with agents, and which he can find some different results for. If Yuri Biondi shows up, Yuri can also talk about things. I don't know if he's going to be here or not today. But with that, I'll turn it over to John. And once again, John will present for roughly half an hour, a little bit more or less. And then at the end, I hope to have time for some conversations after John talks and then Jack talks. So I'm going to stop sharing my screen here. And you should be able to share your screen, John, if you'd like to.
Okay. Okay, can everyone hear me okay and see my slides?
Sure can.
Okay. All right, so first off, I just want to say thank you to the organizers for putting this all together. Excited to share some of this work on, as Rob said, agentizing a classical model that I've been working on with a couple of my co-authors, Roberto Veneziani and Naoki Yoshihara. So I'm going to start out by giving a little bit of background on what exactly the classical model that we're agentizing is, because it's not necessarily something that's commonly used in economics, and particularly may not be known outside of economics, even if people are very inclined towards interdisciplinarity. And so what we're doing with this agentization is we are taking the classical Marxian theory of prices, and which consists, so there's an argument that the classical political economists Adam Smith, David Ricardo, and Karl Marx kind of thought of or envisioned capitalist economies as large systems with high degrees of freedom and open-ended dynamics. And they considered equilibrium prices to be centers of gravity for fluctuations in market prices. These centers of gravity would only really emerge over a long period of time through the decentralized decisions and interactions of agents. And conventional formal treatments of classical prices or classical Marxian prices really don't kind of capture these kinds of dynamics. The formal treatments generally work from the long period prices or the center of gravity or equilibrium, just as an analytical tool. So what we're doing, like I already said, is we're building an ABM to try to capture the price formation that's described by the classicals and Marx, and to capture these open-ended dynamics through a pretty careful extension to the conventional approach. And what that means is we're going to kind of start from the standard formal treatment of classical Marxian prices, and we're going to stick to as close as we can to rational behavior to see what kind of results we get through this kind of first pass at agentizing this model. Now, there's been some earlier work that's closely related to this, some which I did. I built an agent-based model of a smaller scale, very kind of specific case of classical prices as part of my dissertation a while ago. There's also a similar model that's been done by Ian Wright. Now, in a lot of senses, an agentization of classical Marxian prices is pretty close to, in spirit, or at least one precursor, it could be considered a lot of the work in the cross-dual dynamics literature by people like Peter Flaschel, Willy Semler, and Dumanil and Levy. Now, there's a tradition that views there's being strong similarities between the classicals and Marx in terms of their theories of price and value. And this is typically based on some notion of what's known as a labor theory of value. And this can be illustrated with a very simple scenario. Usually we do this using Adam Smith's thought experiment of the early and rude state before the accumulation of stock and land and all of this. And this is kind of a well-known example from Smith, where he's talking about some abstraction of a society of hunters, or in a more general case, commodity producers. They have access to any non-labor inputs that are needed for production, or labor is the only input in production. So you have many commodity producers. All they need to do is decide what they're going to produce. They just produce one of two goods at a time, either beaver or deer in Smith's example. And they then exchange with each other across these sectors, because each of the producers still demand, even though they can produce only one good at a time, they still demand both. If prices aren't consistent with the labor time that's needed to produce the goods, then producers are going to have an incentive to migrate across sectors until these prices really do align with the labor times embodied in the goods themselves. And this movement of producers is considered to be ongoing, and the labor theory of value equilibrium, where prices are going to correspond to these labor times, that really only emerges as a center of gravity for ongoing movements in market prices. This simple example can be generalized to the case of many goods, and to include capital. And once we do that, then we would no longer be looking at just direct commodity producers. We'd be looking at classes of workers and capitalists. who would migrate across sectors until wage and profit rates equalize. And this is kind of what's known as the classical competitive process. Equilibrium prices in the more generalized scenario, these equilibrium prices ensure a uniform profit rate across industries. Now, there are a lot of issues with the labor theory of value, but that are well known. But the classical prices that ensure a uniform profit rate across industries, these are still a pretty helpful or useful analytical tool. So the standard treatment of classical prices in an n-good world typically assumes you have a linear circulating capital economy, you have a price vector P, and a matrix A, which denotes the capital requirements for production, or the non-labor inputs that are needed for production. You have a vector L that denotes the labor or direct labor requirements for production for a specific good or in a specific industry. And then you have W and R that respectively denote wage and profit rates. We can then write down classical competitive prices as such, either the first equation on the left, where wages are paid prior to production beginning, or in the version on the right, wages are paid after production concludes. We're going to the model we look at, we're going to look at the first case where we have wages paid prior to production commencing. So these prices here, these are the equilibrium prices, classical Marxian prices that we are going to then now develop, or we've been working on developing an agentization of. So constructing a simulation with many agents, so agentizing this requires, carefully thinking through a few things. The first is we have to basically build a model with many agents who are going to be making decisions about production, exchange, and how to allocate productive capacity across multiple sectors of the economy. Now, the formal treatment of classical Marxian prices leaves quite a bit out. And so we have to fill in some gaps to agentize this model. The first and probably the biggest gap that we have to fill in is some model or some procedure for exchange. In the classical Marxian framework, the details of how agents or producers actually exchange between each other is really unclear at best. There really isn't any detail about how they thought that actually worked. It is just kind of implied that exchange works well enough that we're going to see these equilibrium prices emerge over this, very long period of logical time. They don't give a time frame about what that actually looks like. It's more meant long enough. They're kind of folding the time period or the length of time into the abstraction or the level of abstraction that they're making when they're kind of thinking through the formation of equilibrium prices. So the second gap we have to fill in is, how do agents actually make the decision about allocating productive capacity across industries? In something like the cross-dual dynamics literature, you have a mechanism for capital allocation based on profit rate differentials. And this is and we're going to have some version of this in our simulation that we built, and that I'll see in a few slides. And the way that the classicals kind of talk about this is that capital is going to migrate in response to profit rate differentials in some way, but there isn't really any detail provided beyond that. Then a third issue has to do with kind of the timing and sequencing of the simulation, right? So the equilibrium prices are the prices for all goods, whether they're serving as wage goods for consumption or if they're serving as capital goods for production. So then this begs the question of, how do we, think about, do all these markets meet all at once? Do they meet in sequence? So that's also another issue that kind of pops up as soon as we start thinking about an agentization or a simulation of this particular model of prices. So to begin our agentization of the classical Marxian prices, what we've done is we've built a two-good simulation. So we start from a two-commodity or two-good world. we have a linear economy with a Leontief technology. So we're going to use that same A&L from a couple of slides ago, but just for only two goods. We denote time periods by the subscript t, and our simulation is going to run for some length of time, uppercase T. The set of agents, with individual agents denoted by nu, is partitioned into capitalists and workers. And where we have the number of capitals denoted by the non-script uppercase n. And this tells us the number of capitalists operating in particular sector I, either sector 1 or sector 2, during any given time period t. Each agent possesses, in the set of capitalists, a subset of capitalists, possesses some endowments denoted by omega. And the way we start out our simulation is agents are actually only going to have one of the two goods in their endowment. So they're going to hold none of one good, or the good that they kind of have not previously produced, or this is going to help us determine which side of a market they wind up on once they actually exchange. So any agent nu has endowments omega. Workers in our simulation so far are purely passive, and they just kind of inelastically supply labor at a given subsistence wage denoted by a B. Workers do not save or accumulate. Capitalists are going to invest all profits, and they do not consume. We also assume that wages are paid before production. What this does, that assumption does, is that allows us to basically construct this matrix M that captures all of the production requirements, both the non-labor inputs in the A matrix and the necessary labor inputs denoted by a BL term in the M matrix there. Lowercase m sub I is going to denote a column of that M matrix, or kind of the technology that needs to be operated in a particular industry by any agents or any capitalists who are operating or producing the good for that industry. At the start of any time period, our capitalists are going to enter the market with their endowments in order to exchange to have the inputs needed to operate the technology and produce goods. So at the start of any time period, capitalists are also committed to operating in one of the two sectors at the outset of the time period, and they stick to that. They don't decide to switch which sector they produce in the middle of a time period. They only make that decision between time periods. So any capitalist operating in sector I, or committed to operating in sector I, is going to enter the market with their endowments and with some expected prices, P with a superscript E. These expected prices in the first time period are randomly determined and consistent with a positive profit rate in the sector to which the capitalist is committed to operating in. And these are also constructed such that the profit rate, or the expected profit rate that the capitalist has, is higher for the sector in which they're committed to operating in than the other sector. We also normalize all the prices to 1. So all prices, both expected prices and the actual exchange prices that we'll see in a little bit, they all sum to 1, just to keep things simplified for us. Any agent is going to have input demand Y, determined by the technology in the sector in which they're operating and their current level of endowments. We use this input demand to then determine individual agents' trade functions, so denoted by tau. Any agent who has a negative value for one of the entries in this vector tau, that means they're going to be a net supplier of that particular good. And then for any agent who holds 0 of a particular good in their endowment, they're going to have positive demand for that good because they need some of both goods in order to operate the technology in that sector and to produce goods. So we use these trade functions tau to determine which side of the market agents are going to be on. So the exchange algorithm goes as follows. We kind of check these trade functions tau and partition the subset of capitalists into sides of the market. We then randomly pair agents supplying good I with agents nu supplying good I with agents mu supplying good j, who are thus then also demanding good I. Any agents who are unpaired, because we can have an uneven number of capitalists committed to each of the two sectors, any unpaired agents are temporarily placed in another subset U. We then check the pairs of endowments. We check the endowments of the pairs nu and mu to be sure that an exchange is possible. And if there is a case where an exchange is not possible, then those pairs are added to that other subset U. So during each time period, we then also make one attempt to rematch the agents in that subset U to see if there are some additional exchanges that are possible. So the viable pairs of traders, nu and mu, that we draw from the subset of capitalists, they then exchange at prices P, with the superscript nu and mu to denote the pair, such that there is no excess demand for good I between these two agents. So we determine prices according to this equation here, so that we have there's no excess demand for that good I between the two agents, which then conveniently by Valra's law means we can then figure out, we then also are not going to have no excess demand for the other good J. So we use these prices P to update the capitalist trade functions tau to determine the quantity of good I or good 1 changing hands, which then also allows us to determine the quantity of good J or good 2 changing hands as well. And so the condition Valra's law just essentially means that if one market's in equilibrium, the other one has to be as well in the case of a two good world like we're operating in. So this exchange procedure is going to run until all pairs who can trade do so. Agents who successfully exchange are going to remember their equilibrium exchange prices to determine their profit rate and to then also update their price expectations for the next time period. Agents who complete a trade move on to producing goods during this time period T. Any agents who did not successfully complete a trade are assigned placeholder prices. These placeholder prices are consistent with a 0 profit rate in the sector to which these agents are committed at the outset of the time period. At the end of exchange, agents update their endowments to reflect these exchanges. And then any agents who have successfully exchanged then proceed to producing. So during any time period, agents who have successfully traded use their endowments updated to reflect their trades or their exchanges to produce some quantity of good I, denoted by X, during the time period. So an agent's output vector is denoted by the bold X here. They only produce one of the two goods during the time period, that good that they have committed to producing at the beginning of T. After agents produce, we then update their endowments to reflect any endowments consumed in the production process. And then we also update their endowments to reflect the output that they've produced. Agents who did not successfully exchange and did not produce any goods during the time period carry their endowments over to the next time period. After production concludes, agents are going to then evaluate whether to produce in a different sector or the other sector during the next time period. So an agent nu is going to compare their individual profit rate based on their equilibrium exchange prices or their placeholder prices to the average profit rate in the other sector. So the way agents do this is by using a logistic function. They basically use this to evaluate the difference between their own profit rate and the average profit rate in the other sector. So what they do with this is, once they've calculated this difference, they compare this to a threshold denoted by rho. And if this value psi is greater than rho, they then switch to produce in the other sector during the next time period t plus 1. So any agent operating in sector I, if psi is turns out to be higher than this threshold rho, they then will decide to produce in the other sector, commit to producing in the other sector during the next time period. If psi is less than rho, they're going to maintain their commitment to producing in the sector that they are currently operating in. Any agents who wind up with a negative profit rate, they're at the end of exchange, they automatically switch sectors to the next time period. When any agent who does decide to switch sectors, they update their expected prices for the next time period to be the average prices that are consistent with the average profit rate in the other sector, sector J. So the procedures of the simulation occur in the order that I just presented them. And here's a quick table of our parameters. So we built the simulation in Mathematica, and we have, like I said, we've restricted ourselves to the two good scenario. We begin with 100 capitalist agents. We begin with 55 in sector 1, 45 in sector 2. We have initial endowments that start out pretty small and within a fairly close range. And we initially assume that all agents have the same threshold for switching sectors. So we assume uniform rho across all agents. Now, as I said, in building this agentization, we've tried to stick as closely as possible to what can be considered rational behavior to see, even if we just agentize the classical model in this direction, adhering to this, what kind of results do we get? Do we get results that show some kind of convergence to the classical Marxian long period equilibrium prices? Because it's not unreasonable to think that we should get something like that. So we have some preliminary results so far. We're still working on this. This simulation is still very much a work in progress. So these results are somewhat preliminary. And I'll talk about I can talk about some of the directions we might be thinking about taking this in as we continue working on it. So the first set of preliminary results that we have here, we have some relative exchange prices, basically taking good 2 or sector 2 as numeraire. And in this red line here, this is the average relative, all of the dots that you see here in the diagram, these are the relative exchange prices between the eligible pairs of agents. Relative average market price is this red line here. This dashed black line, this is the equilibrium relative price, prices that are consistent with this equation here, with that uniform profit rate across the two industries. And then in the panel on the right, we have the allocation of capitalists across the two sectors. And so even in this first set of results here, we do get some kind of oscillation of average market prices around the equilibrium. But if we were to draw kind of a center of gravity through these fluctuations, it's not quite at that equilibrium yet. This could be due to some factors that we're still kind of sorting through with the model, or do we have the right switching algorithm? Do we have the right exchange procedure? Things like this. But we do get some oscillation of prices around the equilibrium, but we don't see we don't see anything that looks like convergence to that equilibrium. It's not to say that we should necessarily expect some sorry, let me rephrase that. That's not to say that the only expectation we should have of having rational agents in the simulation should be that we get convergence. We could have kind of open-ended dynamics, but we would hopefully expect that they be kind of more closely around this, long period equilibrium price. Here, all I've done is basically just zoomed in on the prices from that first panel on the previous slide, so we get a closer look at things here. And then down below in panel C and D, I show the average profit rate across the two industries. And one thing that we see here in our results so far is that the profit rate in sector 2 remains quite a bit above the profit rate in sector 1, which could be that this could be due to some question of, are agents really switching in the right way, or is this actually something that is a result where as soon as we agentize this classical model, it turns out it doesn't actually hold up as well as we maybe previously thought it should or would have. Here's a similar result, same results, just for a different simulation run. So you can see that there's some slight differences depending on the run of the simulation, due to the kind of randomness in the initial conditions based on those endowments that because agents begin with random endowments between that range of 0.2 and 0.5. So I'm just going to skip, in sake of time, just to kind of the open areas that we're still thinking about as we continue to refine this simulation and work on it. As I mentioned, there are some different options that we could consider for the exchange procedure. We can also rethink or think further about how agents are going to make their mobility decisions across sectors. We could think about different production decisions. We could add in things like capitalist consumption, technical change. Workers, could be non-passive. That's probably something we would want to have in a larger scale, more developed version of this model. And then also adding more sectors and more industries as well. So I'm going to end here just to be sure that I hope I haven't gone over. I just want to be sure we have some time for any questions and discussion. So thank you.
Thank you very much, John. That's very informative, and always, it always seemed to me in reading Smith and Marx, etc., that this idea of having the profit rates converge due to the motion of the capitalists was so intuitive. It was obviously they're very prominently in Smith and never really questioned by Marx, and so to see you unpack that is very informative. Why don't we take? We are going to have time at the end of this panel for a broad discussion. But why don't we take 5 minutes right now to have a little bit of specific questions about this model? I have Tim's hand up first on my box, so Tim, go ahead.
Yeah, so this is very cool, and I think you're getting. I mean, yeah, this I want to see this. I want to see this keep going. So a thing that stands out to me is the switching, the 100% negative autocorrelation, where they're you get this sawtooth pattern of who's in which industry. That seems like something you want to not have. And I guess the first thing I would try if I were groping my way through a model like this would be to have it not be, if you didn't make a profit you switch, but if the more profitable things were, the less likely you are to switch, and the less profitable, the more likely you are to switch. Where things are very unprofitable, you're very likely to switch. and that could just kind of soften things, so that you get multiple periods to adjust, but you don't always overshoot. Um, that I don't know if that would make, I don't know, I have no idea what that would do to the average price, but it might do good things if the market could actually settle down. And yeah, that would be a way to get the market to settle down. And it would be kind of an imperfect information way to do it, which is kind of in the spirit of what you're doing.
Should I address
go ahead,
questions as they
yeah.
come up, or should we take a batch or?
Your choice.
Oh.
Why don't you go ahead and respond? Yeah.
Okay, yeah. So I think that thank you for that comment. I think that's absolutely right, and kind of very in line with where the conversations between my colleagues and I currently are in thinking about this, because this sector switching routine is it's pretty, it generates rough results with that pattern. And a few options, like kind of one thing would be have some heterogeneity in that threshold for when agents switch. So that's one way to also add a lot more heterogeneity to the agents themselves. And I think that it is also a good idea for us to try something like you suggested, where it's not just comparing where their profit rate is to the average, but they could even have some kind of process of looking at how profitable have they been historically, and would it even be a good idea to switch? Because it could be that you have a capitalist who has a fine profit rate for a number of time periods, and then they have one bad one for one time period and decide to switch, and that maybe isn't the right argument, isn't necessarily right. Maybe
they could
it would
also
be
look
better.
at they could look at a local rather than a global average. Could also be interesting. Would be another way to make things heterogeneous, where people don't have perfect information about the average. They only have more information than their own transactions gave them. Yeah. Well, anyway, fantastic. Thank you.
Very good. Dave, go ahead.
Yeah, so I was a physicist before I came over to the dark side. You talk about center of gravity, and you may be looking at center of mass. And so center of mass, center of gravity, center of inertia takes into additional consideration the dynamics. And you may find, because at the time that many of the people were talking about this, like Smith, Ricardo, and Marx, they weren't necessarily making that distinction. Because you're modeling it numerical, you may have to take that into consideration. So I was just going to pass that on.
Yeah, thank you. Yeah, I think that's a good point about that use of that term center of gravity is kind of taken for granted by, I mean, myself included, a lot of people who work in the classical Marxian tradition in describing how the classicals and Marx thought about this. So I think, yeah, that is an excellent point that we could rethink that too. Is what does that mean exactly, and are we thinking about it the right way?
Okay, one more question before we turn to Jack. Go ahead, Jacob.
All right, thank you. Yeah, this is a very cool model. I was wondering, I might have missed this because there's a lot going on in the exchange mechanism, and specifically the pairing mechanism. Did agents compare prices at all across possible traders, or is it fully random? You just see if it's viable based on whatever that viable metric is?
Yeah, so it's actually purely random, and then there's determined the viability condition is basically we develop a kind of classical Edgeworth box, so to speak, and with their endowments, are they going to even be at a valid point such that there is a set of mutually beneficial trades that they could make, and so it is purely random. We have also had some conversations about whether we should have them do some kind of search procedure, sample expected prices and endowments of other possible traders to maybe maximize the number of possible trades. Because one thing that does happen in the current simulation is the endowments of the agents can get very out of whack, even over shortish time periods, because you can have a situation that is not uncommon in the current setup where agents could complete so you have a certain number of trades that take place during, say, the first time period. You can have an agent who doesn't get to trade during that first time period and then never gets to trade because they just kind of get left behind and left in the dust in terms of their endowment, because the others who do trade and do get to produce accumulate rapidly. So that agent who gets left out of exchange during the first time period or during the early time periods, it is possible that they just kind of sit there idly doing nothing during the whole simulation, because their endowment's never going to have, or it's incredibly unlikely that they're going to be able to have a viable trading partner based on the kind of viability condition we have. So there's a number of things that we want to think through or spend more time thinking through to see, both to get more exchanges happening and maybe improve the intersectoral mobility dynamics and all of these things. But this is kind of a first pass of what happened. Let's stick to, kind of a very boiled down or boilerplate version of rationality and see what happens. And already it does, it is interesting that we then do have to think about these kinds of things in order to have this classical model kind of hold together under an agentization, because that implies that rational behavior, or strictly rational behavior, isn't necessarily consistent with the classical framework.
Right. So just the reason I was asking all that, those are sort of the things I was thinking about, but it doesn't strike me that you could say that this is anything approximating rational behavior if it's just random exchange. I mean, if I go to a market where there's bargaining, I go and check a few different prices. I'll ask this guy what he's selling and ask this lady what she's, and then I'll pick who to trade with. And I don't have perfect information, but I have some information. Whereas this is almost like zero information in some sense.
No, I guess that is more. I guess that is right. Yeah. I think if they were fully rational, they would then search the entire space of agents and find the best matches. Computationally, I think that sounds unpleasant for to run. Well, just if we scale up the number of agents, it could get really, really clunky, really slow, pretty fast, which does, kind of harken back to a lot of arguments made about how, limits to agents, ability to compute information and all of this, and, arguments that have been made about general equilibrium as to whether it even is like something that could be computed or found. And it's an interesting point. I think, we need to think about that more carefully. Like or at least articulate that that's a deviation we have in this. Yeah.
That docking exercise with if it's computationally just super painful, but it works. If you can do it with 10 agents, but you can't do it with 100, that could be really worthwhile. It's like, okay, yes, this neoclassical mechanism works if you only have 10 agents. But clearly you can't do that in the real world. So here's a fully agentized version with local information that actually is possible and is different. That would be a good way to get into that.
Yeah.
Excellent. Well, very good. Well, thank you so much, John, for your fascinating talk. And I hope you can stick around for a little bit, because we intend to have some further discussion afterwards. And there are a couple more questions in the chat that we can go through. So with that, let me turn it over to Jack, who's going to tell us about an ecological model that he's agentized. And, great to see, a variety of different kinds of domains worked on here, both economic, but also, social animals through ecology. So with that, I'll turn over to Jack and take it away, Jack.
Thank you, sir. Let me see if I can do my new trick here. There it is. Okay. You can see my screen and hear me, I assume?
You can, yep.
Excellent. All right. Ooh, I don't have the thing I want. Okay, good. All right. Well, thank you for the invitation. I'm looking forward to the opportunity to sharing this work with you. In particular, I would like to thank the reviewers, the 3 reviewers who gave me some very important comments that I hope if they're here, they will see incorporated in the presentation. What I'm going to do is I'm going to take a couple of slides and explain the title and my motivations, and then we'll get into the agenda, the models, and the results. Okay, so in the very beginning, before there was even language, there was empirical data that humans interacted with and developed heuristics for. I'm going to call that the empirical data. A classic example of that, I think, is on the Pacific coast of Japan. In the hills, you can find a stone monument or that represents the highest level that a tsunami has ever hit. And that, I think, really sums up the human experience pre-language and how important the heuristics are with the empirical world. Then language came, and with it mathematics, counting, geometry, algebra, the calculus, and with that became equation-based models. And that was the Enlightenment, the technological revolution that takes us pretty much up to the 20th century with very powerful models that could explain and predict this empirical experience that we have with equations. Then we get to the current day, and there is a new type of modeling, algorithmic modeling. And I don't know about you guys, but for me, when I took my first agent, gave it a couple of simple rules, dropped it in a simple landscape, and watched the complex behaviors emerge, it was magical, really. And for me, that's a danger sign, right? You don't want to fall in love with a model. If a model doesn't explain the data, no matter how beautiful or fun it is, it needs to be rejected. And so for me, this agentization is the replicating the behaviors I'm interested in, replicating them in the agent-based model from the well-established standard models. And the standard models, in general, should be widely applicable. They should be decades of use. In particular, I'm looking for models that have representations of complex behavior. And if a standard model achieves all those items, then they are going to be historically significant. Once the agentization of the model has occurred, I think it's important to then look at the current equation-based research. When we expand or relax the assumptions and we see differences between the agent-based model and the equation-based model, it's important to understand which is the agent-based model showing something real, or is it failing in this relaxation of the assumption? And one of the things that will indicate, give some confidence to the agent-based model, is if we see current research in the equation-based model attempting to deal with the same issues, which, of course, especially in one of the models I'll be talking about, there is quite a lot of equation-based research attempting to extend the standard model to achieve these additional resolution, let's say. The fascinating thing that came out of this is that the equation-based model researchers do not like algorithmic models. It's very clear that they don't, and the reasons they don't are twofold. One, they don't feel they're getting a mechanistic understanding of what's happening in the process, and they're also a little hesitant to jump in with computationally intensive solutions with highly complex computer simulations. Now, there's kind of an irony about that we'll get to later, but there's also an opportunity here to couch or present the agent-based models in such a way that the equation-based modelers will be able to appreciate them and gain an understanding from our results. Now, the second question, a little jumpy there, is what models did I pick and why did I pick them? And the models I picked were to support the process of natural selection. I'm interested in complex adaptive systems. And of course, as I'm sure this audience is well aware, this applies to social science and economics as well. We're looking for evolutionary optimization, which is an incredibly powerful tool. And I want to use it with endogenous fitness. Often you'll see, and it's a very powerful thing to do, I've done it myself, you take a population, you grow it, apply the fitness function to it externally, and then you make a new population, you make a new population, do it again over and over. And this is a very powerful optimization technique, but it's not endogenous. And so I'm looking for endogenous fitness functions. And so the first standard model of a population with endogenous fitness is, of course, a discrete logistic growth equation. It's the struggle for existence, right? The agents or the individuals in the model are dying, they're struggling, trying to survive, and they're trying to reproduce. And that is the first standard model I want to take a look at. The one I use is a discrete var-host process with time delay, and that has the additional interesting behavior of bifurcating into different regimes from a level population to oscillations to chaotic regimes. Now, of course, if we're going to do evolution, the second thing I need to have is inheritability. And so that brings up the modeling of population genetics. And in particular, this is historically very interesting because, if you'll forgive me for a moment to talk about this, at the beginning of the 20th century, Darwin's evolutionary work was 50 years old. Mendel's work had just been rediscovered, and evolution was considered to be a reasonable theory, but there was a lot of controversy about how you could have a gradual evolution because of the loss of diversity in the population. So the first result that helped push the gradualists, as they called them, along was Hardy and Weinberg showed that in a very large population, you could write deterministic mathematics that shows for a neutral allele, or let's say a haploid with two alleles, a single gene with two alleles, the alleles will remain in the population and will not disappear. So that was supportive of the gradualists, as they're called. But in 50s, or actually in the 30s, and then the Wright's paper in the 50s was the first significant one, there was a discrete stochastic model. If you use a finite population, then you need to have a stochastic model, which they call birth-death models. And in these models, we find that it's a stochastic process with an absorbing boundary. So one of the alleles will disappear. It's just a question of time. And so this was, once this was modeled, they realized that we need to understand how long this takes to see if, in fact, the gradualist theory could continue. So that's the second model that we'll pick to support this region. I see. Okay, so there's three models we'll talk about. It's the agent-based model, which is a simplified version of Epstein and Axel, 1996. And what I'm looking for is a minimum model of a system so that I can tease out those things that are essential for the natural selection and the evolutionary optimization of an exogenous Okay, so the single species logistic growth equation, we will replicate the population. And what's interesting is the single species logistics growth does have a parameter that specifies how quickly the population will grow into its new environment and how much the population overturns or has a death rate at the population level. When we relax the assumptions, two interesting things come out. One, of course, is equilibrium. There is a much different type of equilibrium for the agent-based model than there is for the equation-based model. And the extinctions, which occur in both models, are significantly different. And then we'll take, as I said, we'll take a look at the current research. The second model is the discrete stochastic models of population genetics with a finite population. These are often referred to as birth-death models. And what we're going to have to do there is we're going to have to map the population dynamics inside the agent-based model to the birth-death statistics that the stochastic models use. And then we'll take a look at neutral allele fixation probabilities and times. As I mentioned, historically, the probabilities of fixation are an important measure, and for the support of Darwin's evolution, we needed the fixation times also, which was a much more difficult problem. The agent-based model allows us to explore these probabilities and fixation times across a wide range of growth rates, including what we'll see as changes in the regimes of steady state, oscillatory, and chaotic. Then at the end, I'll add weak selection, and this is actually, I got a little bit of sociology in here. I add a gene that has two alleles, an introvert and an extrovert gene. And what happens is when there's a tie in the algorithm that selects where the agent should move to next, which is the most food in the closest distance, if there's two targets or more that are like that, then this gene kicks in and it says whether you prefer to go to the target that has more surrounding agents or to a target that has less, introvert and extrovert. And then again, we'll look at the current research. We'll have a discussion, and in the appendix, I have the equations for the conservation of resources. Okay, so the Epstein and Axtell model, excuse me, has identical agents, a flat landscape, and the results I'll be showing for you here, metabolisms of the agents are 75% of the maximum capacity of the landscape cell. And what that does is it runs a surplus economy for the agents in that if they get to a cell with the maximum resources, they'll consume 3/4 of it right away, but they'll have a resource left over, which will be a surplus. There'll also be the parameter that defines the stochasticity of reproduction is what I call the infertility variable here, which is related to the probability of birth. So if a agent is alive, he has the resources to reproduce, and there's space to put the new agent, the reproducing the child, into a neighboring cell, then we roll the fertility die, and with some probability it will or will not reproduce. And what that does is that drives the excuse me, the intrinsic growth rate of the system as a whole, which will be important for the logistic model. And with a surplus, we have a higher carrier capacity than we would if we used hand to mouth, where the maximum resources are the same as the agent. So here you can see I have a graphic or a control volume description of the model. And this, I think, well, you can see that the resources are conserved. They come in, perhaps you can imagine, the sunshine into the landscape. The landscape grows. The agents forage the landscape for their resources, and then they metabolize the resources. They die with some resources on them. And in this case, we don't use birth cost, but there may be a cost of birth, which also is a resource sink. And then we also have here the surplus. If the agents each individually can build up surpluses and then access them if there's not enough food in their current cycle to survive. In Appendix 1, I've written the equations for this, and what I think is interesting, it's useful for quite a few reasons. One reason is if you don't conserve your resources on every individual step and a sum over the entire simulation, then you've got a bug with your implementation, and that's a very powerful way to find the bug. Secondly, these equations are very descriptive of how the sequencing and the algorithm itself works for the simulation. And that's always been a challenge for agent-based models to be descriptive enough that they can be reproduced. And this is a tool in that box. But finally, which I discovered as I've analyzed the behavior of this agent-based model, is that these equations help understand or give a mechanized understanding of what's happening inside the model and what effects are being driven by what. And I'm suggesting that perhaps this would be a way to bridge to the equation-based modelers, if anyone's interested. You can see it in the appendix. Okay, so here we go. The first model we have is a single species logistic growth model. The continuous form is called the Verhulst model. You see I spell it differently in different places. And it actually has a closed form solution, and the two key variables here are the rate of growth, the intrinsic rate of growth, and the carry capacity. And this in this form, it has a solution. If we look down at the graph, we can see I actually have three different intrinsic rates of growth or fertility parameters on one graph to make it easy to see. Far to the right over here is the slow rate of growth. It takes 500 generations to get up to the carry capacity, and it's pretty steady there. The reason I'm bringing it up now is the dotted line is the intrinsic rate of growth, is the Verhulst equation, equation 1, fit to this ensemble of trajectories, which gives us the intrinsic rate of growth. And then we move on, and then this is the middle one is a 5, a fertility 5, and the far, which is a higher rate of growth, and then the highest rate of growth is far to the left. And you can see in the middle, we start getting oscillatory behavior. And at the far left, we get even wilder behavior. These oscillations are actually of constant frequency. They're just on a log scale. So the equation we'll actually agentize is a Huntington-Wright time-delayed equation, where we discretize the Verhulst equation, and then we add the tau, which is a time delay. They originally did this for animals that had delayed time, like a locust or octopuses, things like that. But it's actually also important for resource, when there's a delay in the effect of the level of the population on the resources available 2 or 3 generations down the road, which is in fact the case here. The reason that this equation is very important is because it shows it replicates both the oscillatory behavior and the chaotic behavior that we see in the agent-based model with increasing intrinsic growth rates. And I think importantly, it's not only a qualitative description, but it's also quantitative, in that with the appropriate selection of the time delay, and then the critical intrinsic growth rate, which is the growth rate at which the discrete equation 2, bifurcates into a different regime from steady to oscillatory to chaotic, is matched by the intrinsic growth rate, which we get by solving the Verhulst equation for the ensemble of trajectories, and that those intrinsic growth rates match quantitatively, which gives us a lot of confidence that the behavior of the agent-based model does in fact reflect this well-known standard model for logistic growth. Now, where does it differ? Well, one thing that happens, which is quite interesting, is this dotted line here represents the time when the standard model reaches level population, which we would then assume is equilibrium. And in this case, the low growth rate, the equilibrium is reached well before the population underneath it is actually at equilibrium. And this also occurs here for the higher growth rate. What's happening, this is a measure of the mean age of the population and the mean age of the oldest 10%. And stunningly, right, we remember on this graph, we reached, this is the 85 here, we reached steady state easily by 1,000 generations. And here, the oldest 10% of the population doesn't reach steady state till 40,000 generations. And so there is a richness that the agent-based model adds to the single species logistic growth modeling that is not available in the continuous model. Now, the second thing that happens, which is very interesting, let me go back if I can, here is in this regime, the highest growth rate regime has the Hutchinson-Wright equation doesn't have is a well-mixed model. So what happens at very high growth rate is the entire landscape fills immediately with agents who consume all the resources. And since the resources grow back slower than the metabolism of the agents, it then crashes and they go extinct almost immediately. But you can see at the same growth rate for the agent-based model, this extinction does not occur because the growth rate is limited spatially in how far the agents can move and how far they can see, and how much food they can get. And so it doesn't immediately extinct, but goes into this wildly oscillating, chaotic population regime, which, if I can carefully, yes. So, oh, I'm sorry. I just wanted to show for a second here. I forgot about this slide. That the surplus of the agents in this history, we can follow the individual agent's history over the time cycles. And here's the guy, Agent Zero, in '85, who took 35,000 generations to finally cough up his surplus. So there's a very small group of initial agents who are very wealthy for a large part of the population, and it kind of looks a lot like the robber barons. Anyway, let's go back to the extinction event. Now, this is the extinction event we were talking about earlier, and you can see spatially what's happening is that the agents will start, one or two agents start in the middle, and then they build a wave and grow out and consume. The dark gray is the resources, the light gray is the lack of resources, and the dark black of the agents. And there's a wave of oscillating wave of agents that go out and consume all the resources and then die. And there's a seeded group of a few agents left that begin the next wave of the generation. And that's the oscillating we see in the graph in figure 1. Now, because it's a stochastic event with an absorbing boundary, eventually there's going to be a case, and this is at generation 158, that in this particular trajectory, that there were no agents that survived behind the wave. And so once the wave goes through, and this is the last step before extinction, there's just a few agents left, but they're in a local desert with not enough resources to survive, and the species goes extinct, even though in the landscape in general, there's a huge source of resources. And so it's a local extinction as opposed to the well-mixed extinction that we see in the equation-based model. All right, so the second model we take a look at, I hope I'm doing all right with time. The second model we take a look at are what are called Wright-Fisher models. And the general result you can get for all of the Wright-Fisher models is that the probability of extinction or fixation, fixation is actually a two-state. Fixation can either occur when the LA takes over the whole population or when the LA disappears from the population. And the probability of that occurring is just equal to the ratio of the LA at the beginning of the population. And we use 2n for technical reasons to match diploid populations, but this is a haploid. And you can see here's the results. The dotted line is is equation 3. And then the data from the agent-based models across the full range of growth rates, from the very slowest all the way across, sampling pretty regularly, all the way up to the highest growth rate. You can see that this relationship holds very well. And just to be clear, so if you start with 20% of the population of LA1, let's say, then there's a 20% probability that LA1 will take over the whole population, and an 80% probability that it will go extinct, and LA2 will fixate the entire population. Now, to go on to, so this was the first study, which was, as you recall, disturbing for the Darwin generalists, because this said there would not be any diversity in the population over time with neutral LAs. But the question then becomes, what is the fixation time? Does that happen in a reasonable period of time? And in order to map the agent-based model to the upcoming stochastic models, we need to show this, recognize this one-to-one relationship between the infertility parameter, the roll of the dice, how likely it is that you will reproduce, and the resultant death rates at steady state for the generations. And so the death rate, if we assume constant population, is equal to the birth rate. And this is actually, if you think about it, a measure of carnage. When we get down to the very high growth rates with the wildly oscillating populations, you can see that the carry capacity is 830. So 500 people on average are dying in this very chaotic population. Agents, I shouldn't say people. All right. So with that one-to-one relationship between infertility and death rate, we can now talk about how we map to the model. And I don't want to take a lot of time on this. Essentially, what's happening is that the Moran model is the easiest to understand. And in a generation, you take an agent from the population and you roll the dice and you say you either reproduce or you don't. And then they roll the dice again and they say you either live or die. So the result for that one agent is either there's nobody left, there's one person left, which either could be the agent itself or its child, or there's two people, which is two agents, which is the agent itself and the child. And that's represented in equation 4 here. We do this for the Moran, we do that once, boom, and that's the generation. And that's useful because it's reversible and it's simple to do. Canning's extended it and said, let's go through the entire agent population and run the dice on this and calculate what happens to each one of them stochastically. Now, what happens is you can then calculate the variance of Y, which is directly related to the death rate, which is why we used the previous slide up above to show what the death rate is in the agent-based model. And then we can use, which turns out to be a difficult equation to achieve, but it's an equation-based model, which shows the time to absorption. Time to absorption is, again, either the LA is extinct or it takes over the population. It's time to fixation one way or the other. And it's a function of this variance, which is a function of the death rate. Now, as I mentioned, Moran does one agent and that's a generation. Canning's does all the agents and that's a generation. So there's a conversion between the two timescales that happens. All right, so let's start with the graph labeled A on the right, as opposed to the graph labeled A on the left. The graph labeled A on the right is, in this simulation, we start with the population at carry capacity, not the single agent that grows up into it, which we did for the single species logistic growth rate. Now, this is with a equally spaced population of LA1 and LA2. And down here, we have the mean death rate, which is the proxy for the intrinsic growth rate, which we got from the other model. And you can see the models of Canning's and Moran and the agent-based models all track very nicely. And the gray are the individual runs of the agent-based model. Because it's a stochastic model, we're going to get a lot of, we have to calculate the mean. And this is, of course, the mean absorption time. And there is good agreement, I would say, especially in the middle where there's reasonable growth rates. Out here at the huge growth rates, we start to see a little divergence here. And out here at this end too, we start to see a little divergence here, which is interesting. We'll discuss that in a bit. Now, on the left, people are very interested in a single mutation LA absorption time. That means I take a full population of LA2 and I have a single mutation. What happens to LA1 when I put it in there? Because what they're looking for is the possibility that mutation will survive long enough to populate or even fixate the population. And in this case, we do very well, again, comparing the agent-based model to the Canning's and Moran models, except when we get down here in the high death rate, the very high intrinsic growth rate. And what's happening here is the stochastic effects of the wildly varying population make the fixation times of the agent this fixation time much less, because what's happening is the LA is just dying out in those wildly oscillating population levels that we see in these chaotic regimes. And this is, of course, remember that the Canning's and Moran models assume a constant population. Okay. Now, the one last thing I'd like to take a look at, I think I'm doing all right in time, is that we'll take a look at a weak selection. Remember, I said that I introduced a behavior modification in the agent, which is either introverted, or extroverted. And you can see then that we can measure that effect on the probability of fixation. And here we have the same probability of fixation for neutral LA we had before, where if you have 10% of the population is LA1, then there's a 10% population that LA1 will fixate the entire population. But with this weak selection pressure, you can see that the actual Fisher-Wright class of selection shows the probability of fixation to be this dotted line, and the actual agent-based model fits very nicely with that, though it turned out to be a bit of a stronger selection pressure, around 0.08, than what I was going for. And so then we have the probability of fixation, and again, the important thing is how long does that take, so that there'll be time for the gradualist Darwinian evolution. And here we can see we do very well with various initial ratios of a half, a quarter, and a zero. But if we go to the single mutation, which is of course important, we can see that the modeling, there is a significant difference between the modeling and the Fisher-Wright model and the thing we get from the agent-based model. And that is because, again, there's not a constant population. There's the wildly varying population at 500, the high growth rate, which says the stochastic effects will drown out the single mutation before it has a chance to fix it. All right, so I think I've pretty much stated all the results already. It does a very good job. We'll do the first one. I'm sorry, I will chop there. The single species logistic growth model does very well. Where it differs is because of the lack of specific spatiality in the equation-based model. I didn't mention it, but it is a density-based growth limited, so there is an overall spatial effect, but not the local spatial effect we're looking for. In the current research, there's no closed form solutions. And even though, so they do approximations, and what's interesting is that even though they don't like the agent-based models, they use the IBMs, which are individual-based models, the same as agent-based models. It's just a biological nomenclature. They use the agent-based models to confirm that their approximations work, which I think is pretty ironic. Okay, finally, there is, for the statistic models, we did even better. The loss of the constant population in the oscillating and the chaotic regimes didn't hurt the model as much as I expected it. And so our fixation time calculations were very similar to the ones we get from the standard model. The current research is also very interested in the effects of population structure on the fixation times. And so what they're using currently, I didn't see any agent-based models at all, but there are a lot of graph theory simulations going on to investigate these same things. And one in particular, Parsons, would start with a population not at carry capacity, and then showed that the neutral LA fixation time was unchanged by these, what he considered to be bottlenecks, and which agrees with the modeling work we did, which is oscillating population. And I think that's it. Oh, here's the equation-based, here's the control volume analysis of the model, which I think is very informative. 13 in particular, equation 13 shows the relationships of the various forces affecting the flow of the resources out of the population.
Excellent. Thank you very much, Jack, for the very informative presentation. Let's take a couple minutes for questions on these, on Jack's talk, before we move on to a general discussion. So if you have a question, raise your hand. Let me mention that John Klein has put in the chat a link to I think a reasonably well-known Simon Levin paper with a co-author on the relation between individual-based models and kind of continuum models, population-based models in ecology. And as some of you will know, Cy Levin has worked a lot over the years on, I would call them general problems of aggregation. That is, how can you go from individuals up to system level descriptions and some of the pathologies associated with doing so. So Sai's work is he's pioneered a lot of this stuff. And he, by the way, Sai is someone who is open to agent-based models. Although we take Jack's point that there are lots of people who are not, certainly. Any questions for Jack specifically? I'll ask one, Jack, since you okay, go ahead, John.
Okay, yeah, no, one of the reasons I posted that is I was just looking at a number of the references, and I have a certain bias because I'm a former student of Sai Levin's, but I also happen to be in his lab at the same time Ben Volker and Mercedes Pasquale, a whole host of people. And I would my main comment is there was just going back to 94 up through, well, starting in 94, there was a very, very active debate about the appropriate level of representation in systems and which representations gave you the most parsimonious representation of a system for a given dynamic. And that was one of the reasons I posted that paper. But my comment is like the Volker Deutschmann, I think was it the Deutschmann paper? That was part of that debate. Is yes, they're using individual based models, and individual based models, I can say, and agent based models, it's doing the exact same thing. It's just nomenclature. I think in this debate, there's just, because I see sort of in your references, there's a whole gap. There was a lot of work going on going back further, but from 94 up through 2000, that I think would sort of inform this whole discussion. But I'm just digesting this right now, so that's all I have to say. But nice presentation.
Thank you. And if you can point me to some of those references, I'd appreciate it.
I mean, I have a long list. I do in the current work that I do. I try and inject that kind of work into what I'm doing, but it's often a heavy lift. But I mean, that's when just looking at that whole discussion about agent-based modeling and in computational social science and where it fits in. Just to me, sort of the tone of the debate in going back to the mid 90s in ecology was not, there wasn't a separate field. It was just one of many theoretical and computational methods in a theoretician's toolbook. And actually that's the reason why I posted that particular paper, because it illustrates some of the thinking of different representations of the system. But yeah, I can pass more references on to you when I get to it. But thank you.
Oh, thank you. And I put my email in the chat so you can get a hold of it.
And let me just mention two historical points. One is, so going back even before that, John, I knew Sai Levin in the 80s because I wrote a dissertation on a topic that was close to what he had done work on, as well as Herbert Simon. And in the 80s, Sai had a postdoc named Yu Owasa from Japan. And so they worked on—
I'm familiar with you.
Right, yes. General questions of aggregation mathematically rendered, right? So even maybe a little bit less, maybe prior to the work about when can an agent be represented when can an individual be represented through an equation, just the general work on kind of when can two equation models even speak the same game, as it were, right? And so it's my sense that there's a lot of deep results there that have never been fully explored or exploited. And but I think it's certainly a useful set of literature to dock to. And let me just make up the final historical point I'll mention is that I have the very definitive recollection of being in Santa Fe in late 92 or early 93 when Chris Langton, who had pioneered a lot of artificial life work, was creating the Swarm ABM simulation system. And I was there with my colleague Epstein, and he was writing Swarm in Objective C, and we had a bunch of discussion about languages and other things, but when it came to what actually to call, it was not at the time, we didn't use the word agent-based modeling. I mean, Chris was using the idea of artificial life a lot, and Epstein and I actually were calling the sugar scan model, we actually called it artificial social life, as if there was going to be only one such model and then that would be done. But anyways, with Langton, I remember asking him, I say, what are you going to call this thing, and discussing it. At the time, Bob Axelrod was there, and Bob Axelrod thought, I remember that he thought that actor-based model was a good way to think about it. And by the way, the word actor had been used in sociology already at that point, and so that was considered. And then, of course, individual-based model was also considered. But Langton had this visceral reaction against individual-based model, and he said, "I'm not going to have what I'm doing labeled with the acronym IBM." Period. He was sufficiently antithetical to kind of large corporate America. He didn't want to have IBM be the label for the paradigm. So maybe he was a little different sensibilities than ecology in that regard. But that's the historical and kind of trivial, but a crucial reason why it's not, why we call ABM and not IBM anyway. Any other questions for Jack before we have about 20 minutes for a general discussion here. When I open this up to be quite broad and to think about what is the value of this paradigm that Jack has just showed nicely of agentizing an equation model. What John showed earlier with agentizing a very well-known class of models that are kind of in linear algebraic form are well understood mathematically, but have these interesting kind of dynamical properties when you try to render them with computational agents. And just to start the conversation off, I'm just going to show two slides. The two slides I'm going to show are first, if we combine IBMs and ABMs by citation counts, along with what in computer science are called multi-agent systems, right? So MAS, ABM, IBM, put them all in the ABM box, okay? And here are how the number of citations have risen over time with a very crude just Google count of how many papers are using the word. So the blue line here are 30 years, 25 to 30 years of how the number of papers has gone from 10 up to 10,000. This is annual counts, okay? And notice that over the same, it's taken game theory, roughly since the 1940s up until that time to get to the same level. Now, of course, game theory is sufficiently ubiquitous in the social sciences that some papers may use game theory with never using our search term, which was game theory. So maybe that we're undercounting that. And then experiments, the pink line here is both experiments and behavioral economics. And once again, this is such a sufficiently mature field that it may be that some papers don't actually say behavioral or whatever. But also this started back in the late 50s with Vernon Smith, and then it got going in the 60s. My main point to say is that there's been this very and this is in logarithmic coordinates, obviously semi-log coordinates here. So we have an exponential growth of these different paradigms. These are there was a field of the social sciences rendered mathematically, and now we have these new approaches coming in to specify better behavior through experiments, to specify kind of strategic dimensions through game theory, and then obviously the computational ones through the ABM. My main point of this slide is to say this: there's been obviously a very productive period of the last 30 years for the ABM. And then my next slide is just meant to be a cautionary tale and say, are we sure we Frankenstein-like, are we sure we know what we are doing with this technology? So I've written here, is ABM too powerful? And of course, the picture is, a chainsaw cutting butter. And so, I mentioned yesterday, normal science proceeds through the adjacent possible. I talked about earlier today a little bit too. And that, revolutionary science is driven by something. Typically, you have something new. You have a new tool and new data. You have a telescope you didn't have before, whatever. And with something new, you can do things that are very revolutionary. And it seems that many early ABMs just said, the heck with the existing social science models. We're just going to jump off and do and posit an entirely new model. And it's and I just wonder if it's a little bit like we haven't been cutting butter with a chainsaw. And when you think about even Columbus, I mean, Columbus the astrolabe had been used for terrestrial navigation for centuries. It was finally adapted to do accurate on seas navigation. But Columbus's error, I'm just going to write here, is something that we live with today. Even Columbus set sail for India, and then he ran into people, and he called them Indians, right? And I mean, this is a moniker that we still are stuck with, 500 years hence, right? So I think that, so the too powerful part of my title here is just that it may be. I'm just going to throw this out that when we limit ourselves to the adjacent possible, and we take an existing model, render it with agents, and then relax it to move to the adjacent possible. I wonder if that may be a way to control ourselves and limit ourselves. Yes, on the one hand, we would not be able to do as revolutionary science as it would be otherwise. But if we avoid Columbus's error, right? We don't just blast off into Never Never Land where we're going to say, let's take the Walrasian model of price determination in economics. Let's put in a network. Let's put in boundary rational agents. Let's put in non-equilibrium dynamics. Let's put in everything, and then say we believe we're going to hit India, right? But in fact, we go off into the economy on Alpha Centauri or something, right? Someplace that we don't even know what it is. So or maybe the only kind of world, the only kind of economy that the Walrasian model would apply to would be a world of AIs. Okay, fine. But is it the case that if we just start relaxing everything, we're going to end up with our world, or we're going to end up with some different world? Anyways, so I just mentioned that just to initiate the discussion and say, of course we want to do as revolutionary science as possible, but I think we want to avoid calling Haitian Americans Indians if we can avoid it. So with that, comments, questions, thoughts, and just stick up your hand or unmute your mic if you feel like it. Go ahead, Andrew.
So, sorry about that. So yeah, so about the idea of it being too powerful, I would add to the fact is more the fact that we shouldn't take ABM too seriously. One of the dangers we've seen in other fields like systems dynamics, Jay Forrester had the belief that everything could be modeled using systems dynamics and try to model the world, in fact, back in the 70s. I would argue that, ABM should be seen for what it is it's an insight. It's a tool. And I think, there's the danger that we take what's coming out beyond that. So that would just be my comment, really, on the power of ABM.
Fair enough. Yeah, fair enough. Steve, go ahead.
Yeah, Rob. So a trivial point, and then a serious one, all in sympathy with what you just said. I'd like to point out it's a great bit of trivia that the French word for Turkey is dinde, D-I-N-D-E, which comes from D''I-N-D-E, meaning from India.
Okay.
So Columbus brought back turkeys. They thought they were in India.
Excellent.
Anyway, yeah, and this wraps around to the comments on your talk as well, and that is we're looking for explanations here, and the thing is that, and if you want to bring in philosophy, there's Quine's great thesis of the underdetermination of theory by the observations, and that doesn't change no matter what kind of mathematics or computing we have. And so what strikes me in both cases, Rob, is that it would be very fruitful to try to bring in some sort of constraints on the kinds of explanations that can be invented or discovered with agent-based modeling, including in the agentization thing, and constraints that we think are in the real world, constraints that we think can be, if they're obeyed, they can be tested. And I don't have any magic formula for this, but this strikes me as it's going to be a necessary thing to address going forward.
Do you think, Steve, that in those domains where we have a lot of data, I mean, clearly those data put some constraints in place, but are those the kind of constraints you're thinking about more, or would you be happier with more kind of logical, philosophical, deductive constraints, I guess?
Well, what I have in mind is suppose we have lots of data, but then one probably wants to look at you're positing causal mechanisms that generate this data. And so you can look at sort of reality-based constraints on what, how far can the agent move? I'm thinking aloud here, but I'm thinking in terms of genetic programming, and it can pile up just scads and scads and scads of functional baroqueness.
Yeah.
But
right.
And the thing is, you want to protect yourself against that. You want to say, yeah, we're gonna look for really creative, surprising solutions. We expect we can find many to explain the data, and now you need to prune it with some sort of plausibility based upon either intuitions. It could be philosophy, but it would be better if it were, sort of physical, observational intuitions about what sort of relationships are possible.
Got it. Yeah, very good. I concur with that. I think that makes eminent sense to me. But right, how we actually do it
is hard.
Yeah. John, go ahead. John Klein.
Yeah, just two comments. I mean, just the atmosphere of sort of in lab, there was just a lot of active debate, and I had to work hard to convince Cy to add an agent-based modeling chapter, because from his standpoint, it was just it has, whatever you do, it has to be clear. He's he's a fan of clarity.
Yeah, right.
And actually, and so I had to work on. I could not have sold the agent-based model alone. It was demonstrating that you could use models at different. So it was the application of stochastic spatial models at multiple scales in the Rocky intertidal, and demonstrating that you could link the models at different scales, and that having the representations at different scales provided insights. That's, at least I believe that's what convinced him. So that's one thing. The other thing I'm thinking about is one of the reasons why the odd protocol came out of the theoretical ecology community was precisely because there were a number of theoreticians, and I mean, I can't speak for Cy, but just in discussions, very much against black box models. So there was a big push. Is like, if you're going to publish, you need to be very clear about your model assumptions. And then my third part is, just following up on the first part, is going forward, and sort of my feeling is agent-based models, I don't think they're becoming more powerful. I mean, too powerful. And in fact, I actually, I'm really excited about the possibilities of taking advantage of these large data sets. And actually, yes, if we can scale, can we use the data to test our hypotheses regarding mechanisms? So anyway, that's all I have.
Okay, good. Yeah, let me just follow up on that a little bit to say that so I've recently been working with Cy on models of fisheries, and so we have one paper about fisheries with a large team, and I'll just report on that one that maybe to tie this session today with my talk yesterday is to say that in the case of certain kinds of fisheries, and I'll just give the specific example we worked on was West Coast ground fisheries. There we had logbook data, UC Santa Barbara has logbook data for every single fishing vessel. These are the big trawlers that go up and down the West Coast in search of Dover sole and rockfish, that kind of stuff. So there's logbook data on a daily basis for many years, going back a decade, with all the gear restrictions, all the gear usage in there, all the catch data is in there, all the GPS coordinates of the fishing vessels in there. So this is another area where I did not mention yesterday, but it's an area where we have huge amounts of data. Right? We literally have the detailed data of every single fishing vessel for more than a decade. Now, let me just mention that. So when it came time to build a model, build an ABM of that, among the ecologists, we had very little pushback on building ABMs that were going to reproduce those kinds of microscopic data, primarily because there was, any kind of simple rational actor model was obviously very flawed, where it's not going to be able to reproduce the same patterns that we found in those logbook data. But then when we also proposed having an ABM of the fishery stock of the fish population, then there was a lot more pushback, because then they're saying, well, look, we've got 50 years of prior art on how to model fish stocks, even though they're well mixed models, etc. We really don't want to necessarily deviate from that. So I just report that it seems like to model human actors with ABM in that domain, we found little resistance. Of course, IBMs are all about modeling individual animal species, individual animals. But it does seem to me that, from my experience so far with ecologists in that world, is that it's just easier to model the humans, particularly when we have data, than to model the animal stock, which was because there's such good models, because there are such well-worn models. There's a lot of resistance to moving against them, which felt to me a lot. By the way, it felt to me a lot like what we encounter in economics, where people who are trained in the mathematics of economics felt to me a lot like the people who are trained in the mathematics of ecology, and were not willing to ditch those models just off the cuff. Okay, Tim, go ahead.
Yeah, hey, I wanted to draw two different kinds of models, two different kinds of agent-based models. There are models that try to explain some phenomena, try to explain why a price isn't stable, try to explain, why people become polarized. And with those, you should really try to base them in theory as best you can, but sometimes you have to make stuff up. You need to be clear about your assumptions, but those models are always going to be a little bit shaky. They may generate insights, but people may or may not buy them. And the only way we get to someday have models that everybody buys is by doing also theory type models that really focus on an individual theoretical thing and show how it works. And for that kind of model, I think this agentization is critical. And I want to put in just a plug for formal docking, that any model in microeconomics and almost any quantitative model anywhere, if usually someone is claiming to think about individuals, and if the individuals behave the way that the theorist says they behave, the model should really do what their math says it does. Now, often they're doing ridiculous things, right? They're knowing everything, they're reasoning perfectly, they're doing stuff that nobody's ever done. But it can happen that you can build agents that do all the things that the maker of the equation-based model says they do, and it really should do that. And then you can start systematically relaxing assumptions and open up this whole new space. I did this in one dissertation chapter with a really simple model a long time ago, but I feel like that is, and you get a good publication out of that, right? If you can do that, it's getting published. So it's good for us, and it also really does start putting a foundation under what we're doing, so that someday we can build big elaborate applied models where everybody agrees, yeah, that's right, I know that's right.
Okay, very good. I think those are all good points. Excellent. Santiago, you're next.
Thank you. I want to concentrate on the first question. Do we really know what we are doing with this technology? First, probably we can say that ABMs can be viewed as transducers of new governing laws for systems. So if we say that it is the case, we now can treat them as mechanisms themselves. And the question is, do we understand, especially where the line between computational and model lies at? I think that is one of the questions that we really need to explore. And for example, do we understand if part of the model, for example, the scheduler work that at the spec group we're trying to do, is part whether of the model or the computational background? And the reason is, for these questions, seems to be that when we introduce computation into the tool making of science, we need to take care of many more factors. For example, of using finite arithmetics, of using compositional laws of the software, of trying to find what is the effect of having certain limits on the machines we run our software. Some of those will be immaterial to the problem, but some of those will be significant. And I think we don't yet understand the point. So probably, is ABM too powerful? Maybe it can become too powerful, but we still need to find, probably the question is, when can ABMs misfire and why? And
those are Those are very good questions, and let me just mention that I'll just say that I mean, not just me, but many of us have asked NSF and DARPA, et cetera, to have a basic research program on agent computing, just because for many of the reasons you mentioned. And I'll just be even more concrete about it, is to say that my empirical experience is that probably something like 95 to 97, 98% of all ABMs are single-threaded computations, right? That is, we give the appearance of parallelism just because the CPU works so fast that it looks like we have many agents moving at once. But of course, the way it actually works is there's only one agent who's doing anything, or maybe one subset, small subset, and most of the other ones are frozen, right, while some act. And so, if we had a perfectly flexible computing apparatus, we would say, well, let's actually give every agent, let's put every agent on its own thread, or its own core, its own process, and then let them interact across those processes, across the threads. But we don't have enough computing to do that in general, right? I mean, yes, if you have you've got a very fancy new laptop with maybe 12 or 24 cores on it, you can have 24 agents on their own threads, okay? But we can't have 10,000 or a million. So right, it is the case that we have examples today. I mean, there are examples. There are known situations where having simply rendering a single-threaded model in a multi-threaded context can give you different results, both quantitatively different, but also to some extent qualitatively. I mean, the examples of that are fewer, but so that's just one example, I think, where I agree with you wholeheartedly. That many foundational things about how we render models with computing, how we render individual actions on only today having a few cores, a few threads, a few processors, that is problematical in ways that we don't understand today. Once again, maybe go back to a comment I made yesterday, in the year 2050 or in the year 2100, when everybody has 1,000 cores on their laptop and you want to model 1,000 traders on the floor of the New York Stock Exchange, well, then that's probably going to be a different kind of model than we would write today. And we don't fully understand, for among other things, we don't have great tools for doing multi-threaded models today. So there are both conceptual challenges, we need a foundational research program, and there are practical challenges. We need better software platforms to make or to render some of the things which you described, to better understand some of the things which you mentioned. On to Jacob.
Yes, I think one way maybe rephrasing the question is ABM too powerful? Is ABM too flexible? And just that, there's this von Neumann quote, I forget if it's 3 or 4 parameters. He says, give me 3 parameters and I can fit an elephant, and give me a 4th, I can wiggle its tail, something like that.
Yeah.
And ABMs tend to have many free parameters, and so there's a risk of maybe overfitting. And connecting to some of the other discussions in this conference, with the inverse generative social science, you can generate multiple potential rule sets that all produce a target macro level pattern. And so I think that one of the nice things, one of the uses, I think, of this agentization approach, it's not just a starting point for making an agent-based model, but it acts as another constraint in that if you have an agent-based model where your agents are boundedly rational, as you increase their rationality, probably the results should get closer and closer to the neoclassical model that assumes perfect rationality. Scott Page talks about this in his book, The Model Thinker, that one of the uses of fully rational agents is it's one benchmark that you can compare against, and having multiple ways of looking at the problem is also useful. So I also don't think it's weird that people might use an agent-based model to validate that the approximations they make in an equation-based model still work, because the equations are often easier to think with. You have a 1 or 2 line thing you can write on a blackboard and think about how things change as you vary parameters, which that might be harder to do with an agent-based model. So yeah, I think having a methodological pluralism and seeing where these things can talk to each other and inform each other makes a lot of sense, and can help constrain agent-based models to prevent sort of going off into Alpha Centauri potentially.
Fair enough. And let me just mention that I think that many economists would share your framing of the issue, and I think that economics had a bad taste for simulation early on through, I was earlier mentioned about Jay Forrester, through the system dynamics models, where there were very few constraints on what parameters could be used. For example, the limits to growth simulations had no prices in there whatsoever. And so I think that people had the sense that you can get anything you want to come out of the simulation. That was kind of an old saw. But I think that it's also fair to say that as soon as you write down in a multi-agent world setting, or as soon as you write down, say, I'm going to have just a bunch of individuals who all have a well-specified set of utility functions, so they all have some well-specified preferences. And then the only kinds of worlds that you're going to look at are ones where people are all mutually climbing their utility gradients. I mean, that's a very severe constraint on what can happen in the model. And so when you're in such a world where everyone's trying to make themselves better off to some extent, not fully rationally, but just by once again, in Lyapunov's function sense, just trying to increase this sum of utilities, then I think that seriously constrains what can happen. But I do take your point that Von Neumann's point about fitting the elephant or whatever it was. I think that an allied point was Ulam being nonplussed by the demarcation of all dynamics into linear and nonlinear. Right? Ulam said, calling dynamical systems partially linear and partially nonlinear is like calling biology the biology of non-elephants and the biology of elephants, right? I mean, this is just too crude a way to frame a very large area.